NEC Article 725 addresses Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. Specifically, NEC 725.136 focuses on the separation of these circuits from other circuits. Power-limited circuit conductors must not be placed in the same raceway, cable, bundle, or other enclosure with conductors of electric light power. Class 1 circuits hazardous classified locations, or non-power limited fire alarm circuits. However, if separation cannot be maintained, the power-limited circuit conductors must be shielded, insulated, or otherwise protected in a manner that ensures that the maximum voltage on the circuit conductors does not exceed 30 volts. Beyond the National Electrical Code, other references provide additional guidance. BICSI 1, the Premises Communications Handbook, in Section 7, Physical Infrastructure, Section 7.3, Cabling Systems, and Section 7.3.1, General Requirements, states that power and signal cables shall be separated to minimize the risk of electromagnetic interference, or ME. Additionally, ISO/IEC 61984-1 Information Technology Cable Management Part 1 General Requirements, in Section 5.31 specifies that power and control or signal circuit shall be separated in accordance with the local codes and regulations. The justification for separating power and signal cables rests on preventing electromagnetic interference (ME) from the power cables from affecting sensitive signal cables. EMI can cause errors, noise, reduced performance, or even damage to the signal cables. Furthermore, in the event of a fault in the power cable, the separation can prevent the high voltages from reaching the signal cables, ensuring safety for personnel and equipment. Adhering to the requirements of NEC Article 725 and other applicable standards such as BICSI 1 and ISO/IEC 61984-1 ensures the proper separation of power and signal cables, minimizing EMI and maintaining the integrity of the system. Let's delve deeper into the specific aspects of these regulations and standards to provide a comprehensive understanding. Firstly, NEC Article 725 provides specific guidelines for power-limited circuits, defining the voltage and current limitations for Class 2 and Class 3 circuits. These limitations are designed to reduce the risk of fire and electric shock. Secondly, the separation requirements in NEC 725.136 are crucial for maintaining the integrity of signal circuits. By preventing power cables from being in close proximity to signal cables, the risk of EMI is significantly reduced. Thirdly, the shielding, insulation, or other protection methods mentioned in NEC 725.136 offer alternative solutions when physical separation is not feasible. These methods aim to block or minimize the effects of EMI on signal cables. Consider the practical implications of these requirements. In a commercial building, for example, power cables supplying lighting and equipment should be kept separate from data cables carrying network traffic. Running these cables in separate conduits or cable trays is a common practice. When separation is not possible due to space constraints, shielded cables or conduit systems can be used to minimize EMI. Furthermore, proper grounding and bonding techniques are essential for reducing the effects of EMI. Grounding provides a path for unwanted electrical noise to dissipate, while bonding ensures that all metal parts of the electrical system are at the same potential. In addition to the NEC, BICSI 1 provides detailed recommendations for cabling systems, including guidelines for cable separation. The BICSI standard emphasizes the importance of planning and design to ensure proper cable management and minimize EMI. The ISO/IEC 61984-1 standard offers a broader perspective on cable management, covering various aspects such as cable identification, labeling, and routing. This standard highlights the need for compliance with local codes and regulations regarding the separation of power and signal circuits. Understanding the principles of EMI is crucial for implementing effective cable separation strategies. EMI is the disturbance caused by electromagnetic fields that can interfere with the operation of electronic devices. Power cables, especially those carrying high currents, can generate significant electromagnetic fields. These fields can induce currents in nearby signal cables, leading to noise and errors. There are several factors that affect the amount of EMI generated by a power cable, including the current flowing through the cable, the frequency of the current, and the distance between the power cable and the signal cable. Shielded cables are designed to reduce EMI by providing a conductive barrier that blocks electromagnetic fields. The shield is typically made of copper or aluminum and is grounded to provide a path for the induced currents to flow to ground. Twisted pair cables are another effective method for reducing EMI. The twisting of the wires helps to cancel out the effects of electromagnetic fields. In addition to cable selection, proper cable routing is essential for minimizing EMI. Cables should be routed away from sources of EMI, such as transformers, motors, and fluorescent lighting. Cables should also be kept as short as possible to reduce the amount of EMI they can pick up. In some cases, it may be necessary to use filters to reduce EMI. Filters are electronic circuits that block unwanted frequencies. Filters can be installed on power cables or signal cables to reduce the amount of EMI that is transmitted or received. When designing an electrical system, it is important to consider the potential for EMI and take steps to minimize it. By following the guidelines in NEC, BICSI and ISO/IEC 61984-1, and by using appropriate cable selection, routing, and filtering techniques, it is possible to ensure the proper separation of power and signal cables and maintain the integrity of the system. The NEC also provides specific requirements for the installation of cables in various environments. For example, cables installed in wet locations must be suitable for wet locations and must be protected from physical damage. Cables installed in hazardous locations must be suitable for hazardous locations and must be installed in accordance with the requirements of the NEC. The NEC also provides requirements for the grounding and bonding of electrical systems. Grounding is the process of connecting an electrical system to the earth. Bonding is the process of connecting all metal parts of an electrical system together. Grounding and bonding are essential for safety and for reducing the effects of EMI. The BICSI standard provides detailed information on cable management practices. Cable management is the process of organizing and supporting cables to prevent damage and to make it easier to troubleshoot problems. Cable management includes cable trays, cable ladders, cable ties, and cable labels. The ISO/IEC 61984-1 standard provides information on cable identification and labeling. Cable identification and labeling are essential for making it easier to identify and troubleshoot cables. Cable label should include information such as the cable type, the cable destination, and the cable circuit number. When installing cables, it is important to follow the manufacturer's instructions. The manufacturer's instructions will provide information on the proper way to install the cable and on the limitations of the cable. It is also important to use the correct tools for installing cables. Using the wrong tools can damage the cable and can lead to problems later on. After installing cables, it is important to test them to make sure that they are working properly. Cable testing can be done with a variety of tools, such as cable testers and multimeters. Cable testing will help to identify any problems with the cables, such as shorts, opens, or impedance mismatches. By following these guidelines, it is possible to ensure the proper separation of power and signal cables and to maintain the integrity of the system. Understanding the technical aspects of cable separation involves several key concepts. Firstly, impedance matching is crucial for signal integrity. Impedance is the measure of opposition to alternating current flow in a circuit. When the impedance of a signal cable does not match the impedance of the transmitting or receiving device, reflections can occur, leading to signal distortion and errors. Secondly, crosstalk is another form of interference that can occur between cables. Crosstalk is the unwanted transfer of signals from one cable to another. Crosstalk can be minimized by using shielded cables, twisted pair cables, and by maintaining proper cable separation. Thirdly, grounding and bonding play a vital role in minimizing noise and interference. A properly grounded system provides a low impedance path for fault currents to flow to ground, reducing the risk of electric shock. Bonding ensures that all metal parts of the electrical system are at the same potential, preventing voltage differences that can cause noise and interference. In addition to these concepts, understanding the different types of cables is essential for selecting the appropriate cable for a given application. Coaxial cables are commonly used for transmitting high-frequency signals, such as those used in cable television and internet connections. Fiber optic cables use light to transmit signals, offering high bandwidth and immunity to EMI. And shielded twisted pair cables are commonly used for data transmission in computer networks. Shielded twisted pair (STP) cables offer improved EMI protection compared to UTP cables. When selecting cables, it is important to consider the application, the environment, and the potential for EMI. For example, in an industrial environment with high levels of electrical noise, shielded cables may be necessary to ensure reliable signal transmission. In addition to cable selection, proper cable termination is crucial for signal integrity. Cable termination involves connecting the cable to a connector or other device. Poor cable termination can lead to signal reflections, impedance mismatches, and increased EMI. It is important to use the correct tools and techniques for cable termination to ensure a reliable connection. Furthermore, regular inspection and maintenance of cables are essential for preventing problems. Cables can be damaged by physical stress, exposure to moisture, and other factors. Regular inspection can identify potential problems before they lead to failures. Maintenance activities, such as cleaning and tightening connections, can help to extend the life of cables and ensure reliable performance. By understanding these technical aspects and implementing proper cable separation strategies, it is possible to minimize EMI, maintain signal integrity, and ensure the safe and reliable operation of electrical systems. These principles are applicable across a wide range of applications, from residential wiring to industrial automation systems. The separation of power and signal cables is not merely a regulatory requirement, but a fundamental principle of good electrical engineering practice. By adhering to these guidelines, you can create systems that are more robust, reliable, and safe. In summary, remember to consult the NEC BICSI 1 and ISO/IEC 61984-1 for specific guidance on cable separation. Consider the potential for EMI in your environment and select appropriate cables and routing techniques. Ensure proper grounding and bonding to minimize noise and interference. Implement regular inspection and maintenance programs to prevent problems. By following these steps, you can ensure the proper separation of power and signal cables and create systems that are more reliable and safe.